Hello and welcome to monochemistry. Today we're going to look at weak acids and weak bases ionization constants, just briefly again to reintroduce it, but then we're going to solve a problem using the equilibrium expressions, the Ka or the Kb of each of these things. In this case we're going to solve a weak acid problem, and we're going to look at how some of the techniques and tactics you would use to solve a problem like this. But just to reintroduce, remember that a weak acid or a weak base are ones that don't dissociate very much. So when you start off with a certain concentration of a weak acid, the concentration isn't going to change very much of that acid. In other words, it's not going to break apart very much into H plus or H3O plus if you prefer, and the other part, which is usually an anion, A minus. And that's going to mean that the ionization constant or the equilibrium constant, they're interchangeable, is always going to be less than 1. The extent to which it's less than 1 depends on how weak the acid is. The weaker it is, the lower this number will become, and same with the bases. So let's start by looking at the two types of problems that you may come across. The two types of problems you may come across are ones where you have to solve for the equilibrium or ionization constant, or ones where you have to solve for the pH. Now in this particular question, you're given the Ka, and you're asked to solve for the you're asked to solve for the pH. And there's a couple other steps that we're going to be asked to do here as well. So let's take a look at how we would solve this problem. Step 1 in any weak acid or base questions is to write a balanced equation. It was given in the question in this case, but it won't always be, and to create what is called an ice table, what is known as an ice table. Now an ice table, we've talked about these before. The ICE, the acronym, stands for initial, change, and equilibrium. Now in the question it told us that we were given 0.50 molar concentration of H2S. That's 0.50 moles per liter of H2S. That's all we really need to start with to figure out the answers to the question and to create our ice table. So we have a reaction here, and we're going to fill in the values. Now I will say this, liquids such as water are never included in the information in the ice table, so we can basically draw a line through that area right there. We won't be using it. And also, we know that we started with a 0.50 molar concentration of H2S, which means we have 0 of these to begin with. And that will always be the case unless it tells you otherwise in the question. Now, with respect to the change, and for these questions, I know in the past we've used moles in these areas, but for these questions, we're going to use molarity, the concentrations of each of these. And you can use either moles or concentration, and you'll get the same answer in the end. But we'll keep the concentration for this particular problem. Now let's look at the change. Notice that the coefficients of all of these particular species are 1. 1 H2S plus 1 H2O yields 1 HS minus plus 1 H3O plus. That means they're all going to change by some factor multiplied by 1. In this case, the factor is going to be a change by x, 1x. If this was a 2 out here, then we would have 2x. If it was a 2 anywhere else, we'd have... But right now, we know that it's only x. Now, why is this being subtracted? Because we know some of this guy right here is going to dissociate and turn into HS minus and H3O plus. So that's why we're putting a minus there. Now these guys are going to get bigger by some factor x. We don't know what that factor is yet, but that's what we're going to find. So down here at equilibrium, the key here is that I plus C is going to equal E. So in other words, 0.50 minus x should go in here. 0 plus x here would give us x, and the same there. Okay, so now we've filled in our table. What should we do next? Step 2 is to write the equilibrium constant, also known as the ionization constant. Now, recall from the last lesson and the beginning of this lesson that the equilibrium constant, or the ionization constant, is the product of the products, the concentrations of the products, divided by the reactants concentration. So in this case, we should have HS minus times H plus, or H3O plus, I think is what I had on the other side, but they're interchangeable. And down here, I should have H2S. Now, the number that was given in the question was 1.0 times 10 to the negative 7. 10 to the negative 7. Okay? So what we're going to do now is we're going to substitute our values, because remember, this is an equilibrium constant, which means we're going to substitute the values of these concentrations at equilibrium. Okay, so you plug in the values, and this is what you'd get. Okay, that's what you'd get, and of course that would be equal to 1.0 times 10 to the negative 7. All right, that's what you get. Now, here's the problem with that. The problem is, and it's not a huge problem for people that like math and like quadratic equations, but the problem is that we're going to get a quadratic equation if we use this, because we're going to have an x squared and an x. And anytime you have a formula of ax squared plus bx plus c equals 0, this right here, for all you math folks, is how you'd solve for x. We really don't want to do that. So what we're going to do is we're going to make an assumption. We're going to make an assumption that this x here is negligible compared to that 0.50. In other words, that x is going to be so small that it's not really going to change that 0.50 very much. Okay? So now we're going to solve for x. Okay, so 1.0 times 10 to the negative 7 is going to be equal to x squared over 0.50, assuming that x is negligible. We'll figure out whether or not it is a little bit later on. So, eventually, we'll figure out what x is. Step 4, now that we can find the pH. Now that we know the x value, we can solve for the pH. And I purposely left that off, because here's what you should have gotten for the x value. The x value should have been 2.2 times 10 to the negative 4. If you got 5.0 times 10 to the negative 8, it's because you didn't square root it. Remember, we had x squared on one side and a number on the other. We had to square root. Okay, so go back and check that. This is the number you should have gotten. 2 significant figures from the question. Now, this, and this is very important, look at your your ice table, and you'll see that x is in fact also equal to the concentration of H3O or H+. Brilliant. Now that we know that, we can find the pH. And that should be molar. Shouldn't forget to put the units in, I'll lose half a point. Anyway, let's find the pH. And the pH is equal to 3.7. And that makes sense, hopefully, because it's an acid, right? Acids should always have a pH less than 7. Doesn't matter if they're strong or weak, they're still going to have a pH of less than 7. Okay, let's do the last step. Finally, the last step is to find the percent ionization. Now, if we get a number that is bigger than 5%, we have to go back and do a quadratic equation. I'm hoping we don't have to do that. So that's the key. If you get a number greater than 5%, then you can't assume that x is negligible. But if you get a number less than 5%, then you can. Okay, so let's try it. What is the percent ionization equal to? It's equal to the H plus concentration, which we just had, 2.2 times 10 to the negative 4 divided by the initial concentration. Let's see what we get. And the final answer is 4.4 times 10 to the negative 2%. Don't forget to multiply your final answer by the 100. I forgot to say that a second ago. And that, in a nutshell, is how you use these problems, or use this information, use these weak acids to solve a particular type of question. There's 2 more examples in the next 2 videos. Hope you enjoy. Bring your questions to class.